Hello, this is Jeffrey Fox again. We will discuss indices, which are sort of core to searching the web, just because we know indices will make life a lot faster. So we've already given an example of this. We probably keep for every document the terms in it, which are labeled by some ID. I mean, if we have a million words, we label them one to a word, term one through term a million. They have locations because we showed you why you wanted to keep locations because locations allow us to do phrases. And you sort originally you find these originally sorted by document ID. Then the index is gotten by sorting these tuples by term ID, and that is a sorting algorithm, or and it's trivial. Except it's not trivial because the data is so big, so you need parallel computing algorithms and merging algorithms. You have to go back and forth between memory and disk in an efficient fashion. One other important issue is updating, in which we know that streaming data is very important, and this is a good example of streaming data. And as data streams in, a new web page comes along, it updates the image. Sorry, updates the index. And we don't want to have to screw around with our carefully designed index, so we might have a sort of two indices, an old index and a new index coming from the data streamed in. Um, So that's one approach. I mean, this is not the only way of coping with the streaming algorithm. You could have suitable hashes which allow you to insert things in the index in an elegant fashion. That's up to you to decide how to do that. Then you have to access the inverted index, and you want to keep this thing in memory. Remember, we want to do is I mean, the last thing you want to do is to go to disk too often. Disks take too long, so you try to keep things in memory, which probably means you use data compression as much as possible to store everything in as fewer bits as possible. You also use parallelism. I mean, a trivial idea was to have one node for all the index entries beginning with A, and another node for B, and the 26th node for those beginning with Z, and so on. That's not the best way to do it, but that's an example of parallelism. As well as parallelism, which is for one query trying to cope with keeping all the data in memory, or is you want replication, namely there are going to be a lot of people trying to search for the word Super Bowl simultaneously, and that's done by having multiple index resources, each of which might be multiple nodes. And a key feature for making these indices efficient is reusing results, because when you type an index today in a modern search engine, it tells you what other people have typed, and you often actually other people have typed exactly what you want. So this caching of queries is pretty important. So reusing by caching is important. We've already discussed phrase queries like the King of Finland. We do that by keeping King and Finland with location and off with location. And then after we've done an index search on King of and Finland, we check whether those results actually have King of Finland in the document. And if we keep location, that can be done very quickly. Otherwise, you actually have to go back to every document having King of and Finland in it and see if King of Finland exists as a phrase. That's much slower. You could, of course, if for particular phrases, actually index the phrases. That's this partial phrase indices, which is the third option here. This is the slow option. Post-processing and storing word positions is probably the most elegant solution. Here's some example of, which again, this is frustrating. When you try to actually get numbers, you have to go right back to the beginning of time. Very frustrating. So this was 7 million queries to one of these. Alta Vista was a famous search engine. It's now disappeared, but it was famous as an early search engine. And this showed you, 4.5 million distinct results out of, and 2.65 million distinct query strings. So 67% of those strings were requested once, and the most popular one was requested 31,000 times. 48% of the pages requested once, and the 50 most requested pages corresponded to 2% of the requests. And so this is this usual funny curve, which is this long tail curve with lots of popular things and lots there'll be a few things which are highly popular and lots of things which are not very popular, with this nice um, hyperbolic curve shape.